Hello everyone. This is the second lecture of week 6. So, in the previous lecture we learnt about the basics of quasi Newton methods. So, it was you use those methods to implement Newton method, but avoid inversion of Hessian, right. And the idea was to update the inverse. So, let us say Hk inverse is Bk, then you update Bk to Bk plus 1 using some simple methods, assuming that the variation between Bk and Bk plus 1 is not going to be too much, right. And we looked at one of those methods, rank 1 correction, right, where we updated Bk plus 1 by adding a rank 1 matrix to Bk, right. So, we got an expression to update Bk plus 1, right, the one that I have boxed in the screen, right. And the algorithm is to follow the basics again, just that you need to start by initializing a positive definite matrix B 0, but otherwise you choose a descent direction, choose the step size and then update Bk plus 1 using delta k and gamma k. Okay. So, that is basically the algorithm, and we also learnt the code, right, the Python code to implement this for quadratic functions, right. So, we generated random 5 cross 5 positive definite matrix, and B was also generated as a random normal vector. We started from a random initial point and initialized B naught as the identity matrix, but then got the answer in just 5 steps because n is equal to 5. You can try that for any higher values of n to for arbitrary positive definite h and arbitrary b and arbitrary starting point x naught. Okay. In fact, arbitrary starting matrix B 0 as well, it has to be positive definite of course, but otherwise it can be arbitrary as well. For all of these you will see that you get the answer for quadratic function in just n steps. Okay. So, that is the good part about rank 1 correction. Okay. I would like to indicate one more property of rank 1 correction in quadratic functions. Okay. So, let me actually print H inverse and let me also print B. Okay. Let us check what you get. So, the first matrix that you see here is the H inverse matrix. Okay. So, the random H that we had created at the starting of this code, and this is the B matrix that has been attained starting from the I identity matrix. So, we update this in 5 steps and we have got to this matrix. You can see that both of these matrices are exactly the same. What does that mean? When you start with a quadratic function and start updating the B matrix, okay, in n steps, in exactly n steps you reach H inverse, okay, for any arbitrary H and any arbitrary B that you start with. Okay. So, that is another property of rank 1 correction that I wanted to tell you. Okay. So, we will actually prove both of these facts now. Okay. So, I have 2 claims. Okay. One is that so I write this as a the first claim is that if we minimize f of x equal to half x transpose h x plus b transpose x plus c, of course, I mean presence or absence of c does not matter in this, I mean you might have realized this by now. Using rank 1 correction, we attain the minimum or the minimizer in at most n steps, that is x n plus 1 equal to x star. Okay. So, this is one of the claims, yeah. So, I should write H positive definite, yeah, otherwise it is meaningless. So, that is one of the claims. The other one is Bn is actually equal to H inverse. Okay. So, yeah, let us actually prove both of these claims. Okay. We will actually prove it under some mild conditions. Okay. So, yeah, so recall the quasi Newton condition, which is b k plus 1 gamma k equals delta k, right. So, this is the quasi Newton condition that is boxed here, b k plus 1 gamma k is delta k. Okay. So, what does this actually mean? This implies that b 1 gamma 0 is delta 1, right, sorry delta 0, and b 2 gamma 1 is delta 1, b 3 gamma 2 is delta 2, dot 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 b n gamma n minus 1 is delta n minus 1. Okay. So, that there are just n equations that we have if beta k plus 1 gamma k equal to delta k is given to us. Okay. I want to ask if the following holds. What is that following that I am looking for is, so yeah, b 1 gamma 0 equal to del 0 is fine. So, is b 2 gamma 0 equal to del 0, is this true? We do not know, we will have to check. And similarly, is b 3 gamma 1 equal to delta 1 and b 3 gamma 2 equal to delta 2, are these true? Again we will have to check. And finally, dot 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 is b n gamma n minus 2 equal to delta n minus 2, is b n gamma n minus 3 equal to delta n minus 3, dot 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 is b n gamma 0 equal to delta 0. So, I should have written 0 here, sorry, yeah, is b n gamma 0 equal to delta 0. So, I need to check if these conditions hold or not. I mean, I may either conclude that they hold or they do not. Okay. So, let us nevertheless go ahead and check if these hold. Okay. Yeah, I am basically going to prove that they hold. Okay. So, this property what I have written here, right, this is actually called as the hereditary property. Okay. Just to note. So, yeah, I mean if all of these hold, then they I mean the matrices B is said to satisfy the hereditary property. Okay. So, fine, let us go ahead and prove this, prove that the B's that we have constructed B 1, B 2 dot 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 B n, okay, they satisfy this hereditary property. Okay. So, we will prove this by mathematical induction. Okay. We will show that B1 B2 dot 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 Bn satisfy the hereditary property. And we will use induction. Okay. I will write that by mathematical induction. So, we should first check if B1 gamma 0 equal to delta 0. Yes, that is very clear from the quasi Newton condition itself. So, this is true. So, assume Bk gamma j equal to delta j for all j equal to 0 1 dot 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 k minus 1. Okay. We now show that Bk plus 1 gamma j equal to delta j for all j equal to 0 1 dot 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 k. Okay. So, let us check. Note that Bk plus 1 is Bk plus 1 gamma j is Bk plus delta k minus Bk gamma k into delta k minus Bk gamma k transpose gamma j by delta k minus Bk gamma k transpose gamma k. Okay. Oh, I am sorry, yeah, there will be a gamma j here as well. So, it is Bk plus all of this, and you will have a gamma j outside. So, if I bring it inside, you will have Bk delta j plus all of this, right. But we know that Bk delta j is gamma j if j is not equal to k, j equal to k we will deal with later. Okay. So, this is for all j equal to 0 to k minus 1. Okay. So, but Bk gamma j is actually delta j. Okay. So, delta j plus, okay, so you have a lot of things here, delta k minus beta k gamma k by delta k minus Bk gamma k transpose gamma k, and we will deal with the last case alone, delta k transpose gamma j minus gamma k transpose Bk gamma j. Okay. So, yeah, one thing to note here is that gamma j is Gj plus 1 minus Gj. Okay. And since we have considered a quadratic function, recall that yeah. So, we are actually considering a quadratic function. So, Gj plus 1 will be h into xj plus 1 plus b, and this will be minus h into xj minus b. So, these cancel. So, you have h into xj plus 1 minus xj, which is h delta j. Okay. So, gamma j is actually equal to h delta j, where h is what we have defined here. Okay. So, that is one thing you should note. So, now let us compute what this actually is. So, delta k transpose. So, delta k transpose gamma j minus gamma k transpose Bk gamma j is, so I will write for gamma j I am going to replace by h delta j. So, you have delta k transpose h delta j. Okay. And for gamma k transpose I will write it as delta k transpose h. Okay. So, that is delta k transpose h, and what is Bk gamma j? We have already assumed that Bk gamma j is delta j. So, that is delta j as well. but delta k transpose H delta j minus delta k transpose H delta j is 0, right. So, therefore, you can see that this whole term this whole term becomes 0. So, you have bk plus 1 gamma j is delta j. Therefore, bk plus 1 gamma j is delta j for all j equal to 0 to k minus 1. Okay. So, that is only until k minus 1, but what about k? For k we already know the answer, right. So, bk plus 1 gamma k is delta k was the first quasi Newton condition, right. So, at j equal to k, bk plus 1 gamma k equal to delta k is the quasi Newton condition. Okay. Fine. So, what this means is that I have proved the hereditary property. We have not come to the I mean what you had claimed, right. So, what we now know is that beta k gamma j equal to delta j holds for all j in 0 to k minus 1, and that is for any k from 1 to n. Okay. Good. So, now how do we actually prove these two claims using this? Okay. So, now let us consider the case when k equal to n. Okay. So, so thus, so I will write that thus b1 b2 dot 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 bn satisfy the hereditary property. Okay. So, therefore, bk plus 1 gamma k equal to or gamma j equal to delta j for all j equal to 0 to k. Okay. So, applying this for n, you have beta n bn gamma j equals delta j for all j equal to 0 to n minus 1. Okay. So, I will put all of these. So, note that gamma j and delta j are vectors, right. So, column vectors of I mean they are n cross 1 matrices so as to say. Okay. So, I will stack them vertically, right. So, if I do this bn gamma 0 gamma 1 gamma 2 dot 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 gamma n minus 1. So, now I have an n cross n matrix, right, but bn gamma 0 was del 0, bn gamma 1 was del 1 dot 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 bn gamma n minus 1 was delta n minus 1. Okay. So, I know that gamma 0 is h delta 0, right. So, from here, so note this gamma j is h delta j, right. So, I have bn h delta 0 delta 1 dot 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 delta n minus 1 equal to delta 0 delta 1 dot 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 delta n minus 1. Okay. So, if delta 0 dot 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 delta n minus 1 are linearly independent, okay, then B n H has to be the identity matrix, which means B n equals H inverse. Okay. So, if delta 0 delta 1 dot 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 delta n minus 1 are linearly independent, then B n equal to H inverse. Okay. If B n is equal to H inverse, okay, then note that d n is minus B n G n, which is minus H inverse G n, and that is what you have Okay. So, when you use this particular direction minus H inverse G n, you actually get back Newton's method, and because of that you get the answer in just one step. Okay. So, therefore, x n plus 1 equals x star. Okay. So, we have proved both of this, B n equal to H inverse and x n plus 1 equal to x star, but of course under the condition that delta 0, delta 1 dot 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 delta n minus 1 are linearly independent. Okay. So, yeah, that is still there, but nevertheless I mean I am just letting you know that yeah. So, you take any quadratic function in n dimension, okay, where h is positive definite, and start with any arbitrary initial point and start with any arbitrary positive definite b, okay, you will converge to the minimizer in n steps. And note that you have not inverted, but the inversion has happened in n steps. Okay. So, we have I mean figured out a method. Okay. So, when you do something for n steps continuously, you actually get back the inverse of a particular matrix. Okay. All right. So, that is about the rank 1 correction. Okay. Sorry, yeah. So, that is about the rank 1 correction. Fine, but note that whatever we have done here and explained, I mean the theory whatever we have done is when the function to be minimized is a quadratic function. Okay. What if not, right. So, most of the functions that we work with are non quadratic, right. So, what happens if you minimize a function that is not quadratic? Okay. Of course, you do not do inverse, but what about its performance? So, we will again work I mean use the same example that we have been using for quite some weeks, x 1 squared e power x 2 plus x 2 squared e power x 1, and check what happens when you apply rank 1 correction. Okay. So, since you want the particular function, let me search for it. Yes. So, here we have, yeah. So, I will write down as rank 1 correction for general functions, okay. And here I will just copy this down, just that I will have to modify x. Okay. So, I have defined f of x and grad of x. Now, yeah, I will use 1 comma 1 for now, k equal to 0, b equal to I of 2, sorry, and since you have only 2, let me remove all of these. Okay. All right, this is all fine. Yes, now I have to remove this and use backtracking line search. F of x plus alpha d minus f of x greater than c 1 into alpha into grad of x dot d alpha into, sorry, alpha equal to alpha into rho. So, I have to initialize c 1 and rho also. So, let me initialize them as 0.75 and 0.8 as usual. Okay. Okay. So, it has taken 31 steps to converge to the answer, 0 comma 0. Okay. So, yeah, I have done nothing, I mean I have just repeated what I did for quadratic functions to every general possible function, right. So, yeah, f of x was defined as x1 square e power x2 plus x2 square e power x1, grad of x was defined as we would define always, and yeah, we started with 1 comma 1. I chose d as minus bk gk, performed backtracking line search for computing alpha k, updated x, delta and gamma, updated b, and yeah, updated k as well. So, that is all it is. So, before going to I mean we should check what happens if I modify x. Okay. So, yeah, but just before that I told you that I will explain about what I have done here, right. So, this is something I did not do in the last class, last lecture, I will do it now. Okay. So, note that DL and GM are one dimensional arrays, right. So, yeah, grad of x is a one dimensional array. So, B into grad of x will be a one dimensional array, right. So, alpha into D will also be a one dimensional array, right. So, I mean I can print those values just to I mean give you an idea of what is happening. Okay. Yes. So, this is for the last 31st iteration, what was the delta? It was this, okay, and you can see that it is actually a one dimensional array. Okay. So, if you compute the transpose of a one dimensional array, okay, you can see that it is the same matrix. So, transpose is meaningful at least in Python, okay, when it is a two dimensional array. Okay. So, when you actually want to compute delta k minus bk gamma k into delta k minus bk gamma k transpose, okay, that is actually a matrix. Remember, delta k minus bk gamma k is a column vector and delta k minus bk gamma k transpose is a row vector. So, this is an n cross 1 cross n matrix. So, it is an n cross n matrix, but if you cannot find the transpose as a column vector, okay, then I mean this process would actually be like a dot product, right, you will actually get a 1 cross 1 matrix, right. So, that is what will happen if you just blindly write dl at dl transpose, I mean not dl, it is this, right, dl minus b at gm, yeah. So, yeah, maybe I will write it that way, dl minus b at gm and dl minus b at gm transpose. Okay. So, you can see that both of them are the same. Okay. So, if you do this dl minus b at gm at dl minus b at gm transpose, you see that you get a scalar, okay, and that is not what we want, right. So, how do we correct this? You have to modify these vectors that you already have, right, as a two dimensional array. What is so one of them has to be a column vector and the other has to be a row vector. So, how would you do that? So, when I write this colon comma none, right. So, I convert this into a column vector. So, let me show that to you. Oh no, I should have written it using a bracket, yes, and here I am going to do the reverse, which will make it a row vector, okay, and now when I take the matrix product, okay. Yes. So, here you can see that the first one is a column vector, the second one is a row vector. When you take the matrix multiplication of these vectors, you can see that you get a 2 cross 2 matrix. Okay. So, and that is what we were actually looking for. That is the reason I had to do this particular work, okay, because what we have is a one dimensional array, and just multiplying those two one dimensional matrices will not give you an n cross n matrix. Okay. So, it is more of a Python thing, okay, rather than mathematical thing to handle. Okay. So, yeah, you need to understand about this, I mean conversion of one dimensional array into a two dimensional array, specifically a one dimensional array into a two dimensional column vector. Okay. So, that happens by this particular phenomenon, okay, this square brackets colon comma none. Okay. Alright. So, that was something I had to let you know. Okay. Yeah. So, we will continue with this example in the next lecture. Thank you.